Oh, hello, my dear students of class 12. Today we'll be continuing with the first chapter, the solid state. And today's topic for discussion is imperfection in solids. So you know, in solids, in crystal lattice, whenever the repeating units, it may be atoms or ions, they are always added in certain regular pattern. Yes or no? So in perfect solids, you have this arrangement of these constituent particles arranged systematically. But whenever there is deviation in this arrangement of the constituent particle, then what happens is the imperfection in solid arises. So today we are going to discuss about imperfections in solids. So as I told you, imperfections or defects in a crystal is a departure of the constituent particles of the crystal from its regular position in the lattice. That means, in simple language, the particles, the constituent particles, they deviate from its regular pattern. Okay? So there are two types of defects, the point defects and the line defects. And in our syllabus, we are going to discuss about point defects. Now, point defects, it arises because there is irregularity in the arrangement of the constituent particle, that is atom. Now, these point defects can be further classified into stoichiometric, number 2, non-stoichiometric, and impurity defects. So let's discuss them one by one. So we are going to discuss about point defects. Now these point defects are of three types: stoichiometric, non-stoichiometric, and impurity defect. Okay, so stoichiometric, non-stoichiometric, and impurity defects are the three classes of point defects. Now we are going to discuss about stoichiometric defect first. Now, whenever there is defect in the crystal lattice and it does not affect the stoichiometry of the compound, then those defects are known as what? Stoichiometric defect. So the point defect that do not disturb the stoichiometry of the compound is known as what? Stoichiometric defect. Now there are two types of stoichiometric defect. Number one is vacancy defect. The number two is interstitial defect. So we are going to discuss about stoichiometry. Now this is again further classified into two types. The number one is vacancy defect. Vacancy. The other one is interstitial defect. So the name itself suggests vacancy. Suppose you have a regular pattern of this constituent particle. These are the arrangement of constituent particle. Okay. So in both the types, you have what? Regular position for this particle, constituent particles. Okay. Now, in case of vacancy defect, what happens is like these are occupied by the particles. The ones which are shaded are occupied by what? These are the positions, and these positions are occupied by the particles. Okay? Now, in case of vacancy defect, what happens is one or many of such places will not be occupied by this constituent particles. Like this position was supposed to be occupied by the constituent particle, but is not. Okay? Similarly, you can have this position not occupied by the particle. Now, in this arrangement, can you see that these two positions are not occupied by what? The constituent particle. And these two such sites are known as what? Vacant sites. And this arrangement, such arrangement in which there are some empty spaces in the arrangement of this constituent particle gives rise to what? Vacancy defect. Okay, this is vacant site. Now, in case of interstitial defect, what happens is, like all the positions are occupied by what? All these positions are occupied by the constituent particles. Okay, all of them. In addition to that, now there are certain in this vacant spaces in between this constituent particle. There are vacant spaces. Now these positions will be occupied by some ions, not ions, the constituent particles. Here, like this position is occupied by some other constituent particle. Now this position could be occupied by what? Some other particle. And now since these interstitial positions are occupied by these constituent particles, such arrangement will give rise to what? Interstitial defect. Okay? So, hope this is clear now. An example of this vacancy defect. Okay? Vacancy defect is NaCl. You have more example like NaCl. Actually, NaCl is an ionic compound. NaCl is the example for other ionic type of defect. Now, what you have to remember here is this vacancy defect and interstitial defects are shown by non-ionic compound. So, NaCl is not example for this vacancy defect. Okay, keep that in mind. These two types of defects are shown by non-ionic crystal system of the compounds. Now, let's move on to the type of defect which is shown by ionic compounds. These two are shown by non-ionic. Please remember that. And whenever there is defect in ionic crystal, then that will give rise to another type of defect. We are going to discuss about that. Okay, now. We are discussing about Pseudometric Defect. And here we are going to discuss for ionic crystals. Now in case of ionic crystal, there are two types of defects. One is Schottky defects. Schottky defect. Another one is Frankfurt defect. So Schottky defect and Frankfurt defect. Now these two are shown by ionic crystals. Now, in case of Schottky defect, what happens is the same number of cation. Now here we are from constituent particle we have shifted to what? Cation and anion, positively charged and negatively charged. Why? Because these two types of defects are shown by ionic crystals. Suppose you have this regular pattern again for crystal system. Now, in case of Schottky defect and in Frankfurt defect, what happens? We are going to discuss that. Okay? So, now, in case of Schottky defect, here what happens is these positions are occupied by, say, positive ion, negative ion, positive ion, negative, positive, positive, then it has to be negative, then again positive. Then here, this particular site was supposed to be occupied by what? Negative, positive, negative. Now this is not occupied, means the anion, the negative sign, the anion has left this space and is a vacuum now. So positive, negative, positive, negative. What has left? The negative charge. And from another ion, what will happen? This is supposed to be positive, this is negative, this is positive, this is negative, and this positive once again is not occupied. So what can you see? Here, the equal number of positive ion and the negative ion will leave this crystal system. Okay? Their positions won't be occupied. And as a result, its electrical neutrality is maintained. One positive, from this particular example, what is it? One negative charge is not there and one positive charge is not there. That means one negative, one positive has left this system. And as a result, what happens? Their electrical neutrality is maintained. Now, such defect is known as what? Schottky defect. And in this case, you can see that here there is decrease in density of this particular crystal system. Why? Why? Because you can see that some of the ions, they have left this particular crystal system. So Schottky defect in ionic solids arises in a crystal when the same number of cation and anion are missing from their normal lattice site, and as a result a pair of holes are formed. So you can see that same number of this negative charge and this positive charge they have left, and this will cause decrease in what? Density of this particular system. Now example of this is NaC. Example of this type of defect is NaC. Now then what happens in case of Frankfurt defect? Now in case of Frankfurt defect, what happens is, now positive, these are supposed to be occupied by positive and negative. Positive, negative, positive, negative, positive, positive, and it has to be negative, positive, negative, positive, negative, and now this is supposed to be occupied by what? Positive charge. So this position is not occupied by this positive charge. Negative, positive, negative, positive. Okay? Now, what can you see? All sides are occupied, but in this particular site there is no positive charge. Okay, so this positive cation, positive ion, instead of being placed over here, it has shifted to some interstitial positions. You can see there is space in between among these four spheres. This is known as interstitial position. So now, instead of occupying this side, the positive charge, say, will occupy this interstitial side. Now this side is occupied by what? This positive cation. That is positive ion. Now whenever you have such type of defect, then this is known as what? This is known as Frankfurt defect. So let me tell you the definition. This defect, Frankfurt defect, arises in a crystal due to the presence of a hole in the cationic lattice site. This is the cationic lattice site. Cation is not present over here. Instead of being present over here, the cation occupies the interstitial position. So when such type of defect is there, then that is known as Frankfurt defect. And can you see, has this ion moved out of this crystal system? No, it is not present where it is supposed to be present, but it is present within the crystal system itself. Therefore, the density remains unchanged. There is no decrease in density, and this point is very important. There is no decrease in what? Density, but in case of Schottky defect, since the ions they have moved out of the system, there is decrease in density of the crystal system. And an example, silver chloride. Okay, this is an example. You have more examples in your book, you can refer to them. Now let's move on to the other type of defect, that is non-Pseudometric defect. In your book, you have many differences between Schottky defect and Frankfurt defect. Please learn them properly. Now, number 2, we discussed about stoichiometric defect. Now we are going to discuss about non-stoichiometric defect. That is number 2. Non-stoichiometric defect. Now non-stoichiometric defect. The point defect is the definition for this non-stoichiometric defect. The point defect that disturbs the stoichiometry of the compound are called non-stoichiometric defects. So whenever there is whenever there is disturbance in the pattern of these crystalline particles, then if that disturbance is going to affect the stoichiometry of that particular crystal system, then that is known as what? Non-stoichiometric defect. Now, there are two types of non-stoichiometric defect. That is metal excess defect, and the other one is metal deficient defect. So it has two types. One is metal excess. The other one is metal deficient. Deficient defect. So metal excess, what does it mean? It means that there is excess of some positive ion in the crystal system. Okay? So let's discuss about metal excess defect. Now, this arises, okay, whenever extra cation occupies the interstitial site. Suppose you have this, again, the same type of arrangement, regular pattern. What's supposed to be this one? Okay? Now, let's take outer layer as well. That is 3. Now, in this case, what happens is, suppose these are occupied by cation and anion. B minus, A plus, B minus, again A plus, and this has to be B minus, A plus, B minus, A plus, B minus, and this is supposed to be occupied by A plus, B minus, A plus, B minus, A plus. Yes or no? Now in this type of defect, what happens is, extra cation is coming and occupying what? The interstitial site. Not only the extra cation, but to neutralize that, there has to be one electron occupying one of the other sites. So whenever I write this, here these are the interstitial positions. Yes or no? Now one of these interstitial sites can be occupied by, say, extra cation. Okay, extra cation, that is A positive. This is now, site is occupied by what? A positive. Now to neutralize this A positive, there has to be some electron coming and occupying some nearby interstitial site. Now this is electron, okay, this is electron. Now when this defect is there, then that is known as what? Metal excess defect. Why metal excess? Because you have one extra cation placed over here. Now here metal excess defect can also be because of anion vacancies. Now what happens in anion vacancy? This is one of the way how metal excess defect arises. The other way is, now what will happen is, just listen to it very carefully. Okay? Now this is the other way. But this was the first one. Now you have the regular arrangement. Here also regular arrangement of cation and anion. Now in anion vacancy. Now this is the other way of how this metal excess defect can arise. Now in anion vacancy, what happens is, one of the anion, suppose this B minus is anion, has left the system, is not present over here, but has kept its electron here itself. That means its position is occupied. The cation's position is occupied by now what? Electron. Not the cation, sorry, it's the anion. The anion has left this system, keeping or leaving behind its electron in its place. Then such defect is known as what? Such defect is metal access defect, but caused by anion vacancy. So let me read it out what they have written. When a negative ion is missing from its left side and if in its vacancy an electron associated previously with its left, the defect is called metal access defect due to anion vacancies. Now, the electrons trapped in anion vacancies in metal access defect are called F-center. So this is here, electron is trapped within this system. Now this is known as what? F-center. Okay. Now this F-center, these electrons are responsible for showing color. Why color? Because whenever it gets energy, it gets excited and it radiates some energy, and that will give rise to what? Color for the crystal system. The crystals with metal access defect are generally colored due to the presence of free electron in them. So this electron is supposed is responsible for color of such type of crystal system. Now let's move on to metal deficiency defect or metal deficient defects. Now in metal deficient defect, what you have to remember is when a cation is missing from its lattice side and the lattice metal ion acquires higher oxidation state, the defect is called metal deficient defect due to a cation vacancy. So in case of metal deficient means what? Here, cation is leaving the system. So let me give you an example over here. Suppose you have this crystal system, arrangement of this particular system. So if you have say this A positive, B negative, A positive, B negative, A positive. This is B negative, A positive, B negative. Now suppose this was supposed to be occupied by what? A positive. Now this cation has left. Okay. Now because of that, what happens is you will see over here. This is unoccupied now. It was supposed to be occupied by A plus, that is cation, but is unoccupied. And here you have B negative. Now to maintain the neutrality, okay, electrical neutrality of such defect, what will happen? Its burden will be carried out by the nearby positive cation. That means it was supposed to be A positive. Now what happens is, now its oxidation state will be raised. Instead of just positive, it becomes 2 positive. This is A2 positive. It is because one of the cation over here is missing, and its burden has to be, its responsibility to maintain the electrical neutrality, it has to be taken by nearby cation. So this A, the cation becomes doubly charged, that becomes 2 positive. Okay. Now B minus, and this is now A plus. So this here, if you can understand, that it is A plus 2 or A2 positive here, and here there is no. Here there is no what? There is no cation present. Hope this you understood it. Metal deficient defect. One of the metal, that is the cation, is missing from the site, and one of the nearby cation has to take the responsibility of maintaining the electrical neutrality. Because of that, now this A gets higher oxidation state, that is positive 2. Now, metal deficiency defect may also occur in another way. Now please listen to this very carefully. One extra negative ion may occupy an interstitial position. The extra negative charge may be balanced by some nearby cations present. So now another type of defect metal deficiency defect. This is the first one. There is other way in which this metal deficiency defect can also be caused. Okay, so in that you have a regular arrangement of positive and negative ion. This is A positive itself now. Okay, and this is also occupied by A positive. This is the regular system. Now, whenever an extra electron, suppose in this interstitial position, in this position, say one extra electron has come, E minus. Say E minus has come. Okay. If in this interstitial position, what has been? Electron has come and stayed there. Now, the electrical neutrality of the system gets disturbed. To maintain its electrical neutrality, what will happen is one of the nearby cation, again, it takes the responsibility of maintaining its electrical neutrality. As a result, this A now becomes 2 positive. Because it has to maintain, it has to cancel out the effect of this one electron. Therefore, one of the nearby cation has taken the responsibility of maintaining its electrical neutrality by increasing its oxidation state. If you can understand, then this site, interstitial site, it is occupied by electron, and here, now in this particular part, this is A2 positive. It is not A just positive, it is A2 positive. Please remember this. Okay, so we have discussed about metal deficiency defect. Now let's move on to impurity defect. Now impurity defect is very simple. Now listen. In impurity defect, what happens is like you have a crystal system of one particular type of ions. Now what you do is you put some small amount of, say, foreign particles in that. Okay? Foreign particles means atoms or ions of another type of crystal. Okay? Other type of atom. Then that will give rise to what? Impurity defect. Now if a foreign atom or ion as impurity occupies the lattice site, in place of host atom or ion, the defect is impurity defect. If the foreign atom or ion occupies voids in the structure, now this defect is obviously known as what? Interstitial defect. Now so now we have moved on to this defect. We have moved on to impurity defect. The third kind, impurity. So what do? You put foreign atoms or foreign atoms or ions in one particular system, minute amount of other type of particles in that system. Now this may come and occupy what? Interstitial position. Say, so I'll give you an example. Suppose this is the system of say A plus, B minus, A plus, B minus, this is A plus, not A plus, this has to be A positive, positive. So please remember while doing this arrangement, it has to be positive and negative. So B minus for A plus, B minus A plus. So what will happen? That foreign particle can come and occupy this interstitial position. Say the foreign particle is X. Then such the impurity defect is known as what? Interstitial defect. Now there is another type of defect also, that is, on the other hand, in case if the impurity atom occupies a vacant lattice site, we get substitute some solid solution. That means, say suppose you have again this system is there where we have say A positive, B negative, say this is A positive, this is B negative, this is A positive, B negative. Now this is vacant and say this is B negative. And if that foreign particle, instead of writing X, if I write F, that will be greater, that will be foreign particle. Okay? If that foreign particle comes and occupies this position, this vacant site, then that will be known as what? Substitution solid. Okay? If the foreign particle comes and occupies the what? Unoccupied positions in the crystal lattice, then that is known as what? It is known as substitutional such type of defect where the vacant spaces is occupied by the atom of the foreign particle, then this is known as what? This is known as substitutional defect. And this type of defect where the interstitial site is occupied by the foreign atom. Okay, then that type of impurity defect is known as what? It is known as interstitial defect. So here, one more important term that have to remember is doping. So let's define what is doping. So whenever in such arrangement of the host particles, when the foreign particle occupies such spaces, either it could be the interstitial or it could be the unoccupied space lattice of the system, then that is known as what? Doping. So listen to this introduction of defects by incorporating a small amount of foreign impurity in the host crystal is called as what? Doping. So with this we come to the end of today's discussion, that is imperfections in solid. Hope you'll keep practicing these structures and remember the differences between Schottky defects, Frankfurt defects, metal excess, metal deficient, and all these types of impurity defects. Till then, take care. I'll be seeing you in the next video. Thank you.